Hello all, this is our first lesson in Unit 6, and today we're going to be studying the wave-particle duality of energy and matter. We do have a bookwork associated with this lesson, but it's so short. It's only 11 questions long. So we're really getting there, guys. We're going to make it to the end. And the aim today is how are particles and waves related. Please copy down these do now questions, which I hope that we can answer together in class. All right. So radiation has a wave nature, which you already knew. We've been studying waves. Radiation is just the energy that moves outwards from a point source, which we call waves anyway. But electromagnetic radiation is a little bit special, so you should know a couple of things. First of all, in electromagnetic radiation, there are actually two waves happening at the same time, which is why we call it electromagnetic. So not only do you have this electromagnetic wave, but it's causing two oscillations simultaneously. You are getting an electrical oscillation, which in this case is highlighted in blue. So you have this basically electrical wave that's moving, and then you also have a magnetic wave highlighted in red, which is perpendicular at all times to the electrical wave. So the electromagnetic wave itself is both waves combined, and it's really two oscillations in the field, both an electrical oscillation and a magnetic oscillation. I think probably the most useful thing on this slide for you and the regions, however, is that all forms of electromagnetic radiation exhibit the same phenomena as any other wave. So that would be, for instance, diffraction, interference, Doppler effect, and we explain waves in terms of the periodic phenomena of waves. So yeah, waves act like waves. They have the properties of waves. That was the last slide. But on this slide, I'm going to point out that waves also have particle nature. So not only are waves waves, but they're also particles. Probably the best way to explain this is in terms of a couple of examples. Example number one is a model for how we may be able to get around space in the future. Basically, if you can make this enormous sail, it's called a solar sail, then you can rely on light from the sun or any nearby star that will come in and strike the sail and push the sail in a direction. Now, if light were really only a wave, then would a wave really be able to push a material object? And the answer to that is no. So we know that light not only is a wave, but also has momentum. The light's momentum is transferred to the sail, just the same way as we would study momentum in other units. So the one that I'm showing you a diagram of right now is Icaros, which you might know some Greek mythology surrounding Icarus. His father made him wings out of wax, but he flew too close to the sun and his wings melted. And you might be able to imagine why we would call a solar sail Icaros. But it really stands for Interplanetary Kite Craft Accelerated by Radiation of the Sun. And it's a pretty standard acronym, but it's really lovely, if you ask me. So the other one that we use every day, it's not science fiction, it's science reality, is using the photoelectric effect. I'm going to highlight this one because I want you to remember this one. You do need to cite examples oftentimes in this unit of how you know certain things are true, and this is a great one to cite. But basically, it also says that light has momentum, and it works like this. So you have these two photons, these two light particles that are coming in. They strike this metallic surface, and you can tell it's a metal because you have all these electrons floating around down here. So the two photons come in, they slam into the metal, and they force a couple of electrons to jump out. Now, if these two photons had no momentum, if they were only waves, if they had no particle nature at all, then they wouldn't be able to strike something made of matter and force it to move. So I know for sure that these two photons have some momentum or they wouldn't be able to move the electrons. We use the photoelectric effect all the time. Any kind of automatic door, like anytime you walk in front of a door and it opens for you, that's using the photoelectric effect. It's basically where you are blocking this light path, and that's what sets the whole cycle in motion. So The photoelectric effect demonstrates that light has a particle nature by using light to accelerate electrons. So physicists these days actually believe that energy comes in specific packet sizes. You probably saw a symbol that looked something like this on the previous slide, and I called it a photon. And a photon is really just an energy packet. I think of it sort of like a little envelope, and inside the envelope is energy. While this isn't like the craziest thing I've ever said, it basically is just going to show that there's like a minimum amount of energy, and you can't take a little bit of energy out of the envelope. You have to send the whole envelope, or you could send 100 envelopes, or you could send 1,000,000 envelopes, or any number of envelopes. But the envelope itself has the sort of minimum amount of energy that's allowed. And the first person who really discussed this and brought this idea up, his name was Planck. And Planck was sort of the father of quantum theory. Quant is a Latin root that stands for amount. And so quantum theory is just this theory that energy comes in specific amounts. And that's what these energy packets are. So that said, there's an equation that goes with any discussion about Planck. And it's this really great equation. It says E equals hf. And E, of course, is energy in joules. H is going to be Planck's constant, which we can get from our reference table. But for now, just know that it's 6.63 by 10 to the negative 34 joule seconds. And F is going to be frequency. So if you have like this wave, like an electromagnetic wave, and you know its frequency, you also have Planck's constant from the reference table, you can easily tell me how much energy that wave is worth. So let's put it into motion now. A photon has an energy of 8.0 by 10 to the negative 19 joules. I'll label that. What is this energy expressed in electron volts? So while I don't actually get to use E equals hf to solve this one specifically, I do get to use electron volts, which is really wonderful. I bring it up here. An electron volt is 1.6 by 10 to the negative 19 joules. So let's do this conversion and be on our merry way. So this is the original amount of energy stated from the question. I'm going to multiply it by a conversion factor, which has joules on the bottom and electron volts on the top. I learned that 1 electron volt is equal to 1.60 by 10 to the negative 19 joules. And so I just need to do 8 over 1.6. And I'm getting 5 for that. And then, of course, 10 to the negative 19 over 10 to the negative 19 is 10 to the 0, and which is 1. So my answer is 5. 5 electron volts. All right, quantum theory, the photon. So the quantum is, of course, the basic unit of energy, and we can call it a photon. And it doesn't have any mass, but it does have energy and momentum. And we can use like 2 equations to describe it pretty well. Basically, we have the original equation. The energy of the photon is Planck's constant times frequency. But frequency is also c over lambda. This is just a restatement of the classic equation. C is f lambda. I just replaced the f with c over lambda, which is just a rearrangement. So this equation states that the energy of a photon is directly proportional to its frequency. You can see that right here. So energy and frequency, so they're directly proportional. The more frequency, the more energy. But it also says that it's inversely proportional to its wavelength. So the more frequency, the more energy, but the more wavelength, the less energy. Something interesting to just take in your back pocket with you is that in previous lessons, we would relate energy to mass all the time, like we would use these equations. And we're no longer saying that. A, because the photon doesn't have any mass at all, it only has momentum. But B, because the equation doesn't have mass in it. So just remember that when we're thinking about light, it's really got nothing to do with matter at all. Let's do a sample problem. The energy of a photon is 2.11 electron volts. Let's do 3 things. First, determine the energy of the photon in joules. A simple conversion, let's do it now. I'll start out with my given, and I'll multiply it by a conversion factor that has electron volts on the bottom and joules on the top. And I did learn earlier that an electron volt is equal in size to 1.6 by 10 to the negative 19 joules. And I'm getting 3.3 0.8, I'm rounding a bit, times 10 to the negative 19 joules. Part 2. Let's calculate the frequency of the photon. So E equals HF, and it's going to be really handy that we have converted into joules up here, because the energy stated in this equation must be in joules. But I can basically just rearrange. I need the frequency to be alone. And I get F equals E over H, and I'll plug in variables that I know, which was 3.38 by 10 to the negative 19 joules, solved from earlier, and 6.63 by 10 to the negative 34 joule seconds, which of course is Planck's constant. And I'm just going to divide these parts first, and I get 0.5098. So I'll round that to a 0.510 times 10 to the something, and in this case it's going to be negative 19 minus negative 34, or negative 19 plus 34, and that's giving me a 15. So I'm going to just change this so that it's proper scientific notation. And I got 5.1 by 10 to the 14th hertz. Third step. Identify the color of light associated with the photon. Let's grab an electromagnetic spectrum real quick. So I found this one, and I just basically need to find this frequency on the spectrum. So let's see, 5.1 by 10 to the 14. Too low, too low, too low, close. I think it's going to be in this area somewhere between 5.03 and 5.20. So that's yellow. So earlier we talked about the photoelectric effect, about how a photon or an energy packet could come in and slam into some electrons and eject the electrons, basically just completely transferring the momentum of the photon into the momentum of the electron. But in cases where the, the energy packet is much, much, much larger, then obviously the electron can't absorb all of that momentum. And in those cases, you'll see another interesting thing occur. And that's basically that when an X-ray strikes an electron, the electron does basically take as much momentum as it can, but whatever is left over is a second wave that is sort of like sent out from that original collision, but the wave doesn't have all of the energy that it had before, because remember, some of it went into the momentum of the electron. So when that new wave comes out, it's going to have less energy, which translates into a lower frequency. You can see a diagram of that here. Here's the original wave packet coming in, strikes the electron. The electron takes some of the momentum and some of the energy, but it also releases the rest of the energy, or the remaining energy, in a new wave of lower frequency. So you can find literature support of that idea here. Less energy means that the photon has a lower frequency. So does the photoelectric effect support the fact that photons have momentum? Yes, because it imparts the momentum to the electrons. But in the case when an X-ray will strike an electron, the electron can't absorb all of that energy, and therefore it releases another wave of lower frequency. But why does the wavelength change? So if E equals HF and C equals F lambda, then F equals C over lambda and E equals HC over lambda. So what you can see here is that there's an inverse relationship between wavelength and energy. And one more fun thing you can do involving math here is that you can use the energy of this wave and the energy of this scattered wave, subtract them, and the difference in this energy and this energy would be equal to the energy of the electron. The reason for that is because, of course, the law of conservation of energy. So not only do waves have a wave nature and a particle nature, evidenced by, let's say, the photoelectric effect, there is the other thing, which is that particles not only are particles, but particles can also act as waves. Here's an example. Scientists noticed not even that long ago that if you shoot a beam of electrons at a foil made of gold, and electrons, by the way, are considered particles, they will display elements of waves as they pass through that gold foil. So instead of passing straight through the foil and striking the screen right in the center, they do something much more strange, and that is that they diffract. So A, what does that look like? And B, what does that mean? So it looks something like this. So basically it makes these circular patterns on the field behind the foil. And if you wanted to know why that's weird or why that's not what's expected, just imagine that if electrons really were particles, just particles, then they would behave like baseballs would behave. And if you were throwing baseballs at the foil and they were able to pass through, then they would just strike the screen all in the same place, just like that. They wouldn't bend and move in circles around the screen. So that's what waves do. And of course, the reason why this is important and what this means is that not only are electrons particles, but they are also waves, and that they have wave properties. And so if you are ever asked to provide evidence why particles have a wave nature, please, by all means, use electron diffraction as an example. And with that, we've reached the pair up. I'll make copies of this page for you and this page. Thanks for watching.